The previous video, we showed when a matrix, we showed an example of a matrix that under one basis is diagonalizable or is a diagonal matrix, and under the matrix representation of the linear transformation using another basis is not a diagonal matrix. Now what we're going to do is we're going to explore when is a linear transformation diagonalizable. A linear transformation is T, which is a linear operator acting on V, is diagonalizable if a basis beta for V exists such that each vector in the basis is a characteristic vector for T. And the idea behind this is that we say that if we let beta equal the set alpha 1 through alpha n, with TC or T alpha j equaling Cj alpha j for 1 less than j, which is less than n, then T alpha 1 is going to equal C1 alpha 1 plus C1 alpha 1 plus 0 alpha 2 plus 0 alpha n, which implies that the coordinates of T alpha 1 relative to basis beta equals this vector C1, 0 up to 0. And if we apply T to alpha 2, then we get 0 alpha 1 plus C2 alpha 2 plus 0 alpha 3 plus up to 0 alpha n. So T alpha 2 is going to equal, the coordinates of T alpha 2 is going to equal 0, C2, 0 up until 0. And we can repeat this until we get that T alpha n equals 0 alpha 1 plus the way to 0 alpha n minus 1 plus Cn alpha n, which implies that T alpha n, or the coordinates of T alpha n in basis beta, is 0 up until 0, and the last entry is Cn. Well, this implies that the matrix representation of T relative to this basis beta is going to equal C1, 0, C2, 0, C2, 0. And we're going to get this diagonal matrix with C's on the diagonal, C1 through Cn on the diagonal, and zeros everywhere else. So if we have a set of eigenvectors, then it's diagonalizable. Now, we should know that not all linear operators are diagonalizable. Now, how do we see this? We consider the following example. This matrix here is not diagonalizable. Now, how do I show it's not diagonalizable? I want to show there are not two linearly independent eigenvectors. So I can't create a basis of eigenvectors. Well, that means I have to solve the eigenvectors. So we start by solving the characteristic values. The determinant of xi minus a equals the determinant of x minus 1, 0, x, which equals x squared minus 0, which equals x squared. Thus, c equaling 0 is the only eigenvector. Okay. Now, we solve for 0i minus a, setting it equal to 0. This equals 0, 1, 0, 0 with 0, 0, which implies that x1, x2 equals t0, which equals t1, 0, where t is an element of the real numbers. And if you expand your system of equations and solve it, you can see this. Well, this means, thus, the vector 1, 0 is the only eigenvector of A. So we only have one eigenvector. or the dimension, or what we should say is we have multiple eigenvectors, but the dimension of W, the dimension of this eigenspace, if we let W equal the null space of 0i minus a, then the dimension of W equals 1. Thus, we only have one linearly independent eigenvector. That is, we cannot form a basis using eigenvectors. Therefore, A is not diagonalizable. So we have an example where it's not diagonalizable. Now, what was our condition from A22 that we eventually got to that was our if and only if condition for diagonalizability? Now, to develop this if and only if conditions, we're going to take advantage of something called a block diagonal matrix. When T is diagonalizable, some of the characteristic values may be repeated. So we can write T beta as a block diagonal matrix. T beta equals the diagonal of C1 I D1 through CK I DK, which equals, and it's the matrix C1 I D1, C2 I D2, repeated until we get to CN I, or CK I DK. Now, what's interesting here is the matrix I dj is the dj by dj identity matrix. A characteristic space Cj has a dimension dj, and also the sum of j equaling 1 to k of these dj values equals n, which is the dimension of V. And why does this make sense? Well, each of these blocks, if I have C1 times I D1, it means I'm going to have the C1 on the diagonal D1 times, which means I have D1 different vectors, all of which, when you apply T, you get C1 times that vector back. Same with C2, same up to CK. So the basis for each eigenspace has DI or DJ of these vectors. Well, turns out that because we can do this block diagonalization, if we're diagonalizable, this block diagonalization, we can generalize our definition from here. Okay? But let's explore how, and let's kind of work our way up to that. Well, if A is a block diagonal matrix, then f of x equals the determinant of x minus xi minus a, which equals, we're multiplying these xi minus these ci's d1 times, then x minus c2 d2 times. So we get x minus c1 to the d1 times x minus c2 to the d2, all the way to x minus ck to the dk. And if we look at our previous example, the one that we worked on last time, we get that the matrix representation in our basis beta was 3, 0, 0 minus the 2 by 2 identity. And from here, we can see that f of x does in fact equal x minus 3 times x plus 1 squared, just like our formula tells us. Additionally, if I take the bases for each of these sub-blocks, I take the basis vectors corresponding them to those eigenspaces, I can combine them to create a bigger basis. And we call this concatenating bigger sets. So if beta 1 and beta 2 are disjoint sets, then I can concatenate beta 1 and beta 2 to create the set beta 1, beta 2, which is alpha 1 up until alpha n, x1 up until xk. Now, this notation of concatenation is a little bit abusive. And the challenge with this is if I were to combine sets of sets, and we were to use traditional set notation, beta 1 comma beta 2, the set beta 1 comma beta 2 would be the set containing the set alpha 1 alpha n with the set alpha 1 through alpha k. But in concatenation, I'm not taking a set of sets. I'm just putting them together to create a bigger set. Now, context which will tell us which one we're trying to do. So we actually leave it for the context, for the reader or for you guys to understand what we mean when we say the set beta 1, beta 2. So the context will tell you if you're concatenating them or you're creating a set of sets. What's interesting is if we have two different characteristic spaces for different characteristic values, then the intersection of these sets are zero, meaning we have mutually exclusive subspaces. Okay. To see this, if I take Wi, I can show that 0 is in Wi for all I as, or I guess I should use j. 0 is in Wj for all j as Wj is a subspace for all j. So we've shown that 0 is in, well, what does this mean? This means thus 0 is in the intersection of W1 and W2. So there is something in the intersection. Now, what is in the intersection? Well, if we let x be in W1 intersect W2, then t of x equals C1x, which equals C2x. This implies that C1 minus C2x equals 0. As C1 minus C2 does not equal 0, this implies that x equals 0. What does this mean? If I have two subspaces whose intersection is the 0 vector, the vectors from W1 and W2 are linearly independent. And it means that we can obtain a basis, beta, for W1 plus W2, which if we recall is the set alpha plus beta, where alpha is in W1 and beta is in W2, by simply concatenating bases beta 1 for W1 and beta 2 for W2. Beta is going to equal the set beta 1, beta 2. By simply concatenating bases beta 1 and beta 2. Beta equaling the concatenation of beta 1 equals beta 2. Additionally, the dimension of W1 plus W2 equals the dimension of W1 plus the dimension of W2. This is a direct sum. This gives us our big diagonalizability theorem from MATA 22. Okay. If T is a linear operator and C1 through CK is distinct characteristic values, and Wj equals the null space of T minus Cj, this is a capital Wj, then T is diagonalizable if and only if the determinant equals C minus C1 to the power D1, all the way C minus X minus CK to the power DK, and the dimension of Wj equals Dj for each of these characteristic spaces. Now, what's interesting thing is here, this is a product of linear factors. Okay. Now, this is going to come into a bigger idea that we're going to talk shortly in class. But in A22, all we did is you said we could factor it, and the dimension of each subspace equals the multiplicity. What we did is we gave it a little bit more language. A common way that we could restate this theorem is that we note that each of these CIs is a characteristic value, and we define the geometric multiplicity of these characteristic values to be the dimension of the characteristic space. And the power, di, refers to the algebraic multiplicity. So restating this theorem, we would say that an operator is diagonalizable if and only if the algebraic multiplicity matches the geometric multiplicity for every characteristic value, and the characteristic polynomial factors completely.